Hello, everyone. What's going on? Hi. Hi. Nice crowd today. Good to see you guys. Thank you for coming. This is a late afternoon session, and it's great to see so many people interested in building mobile apps with GraphQL, and we'll talk about React Native, and we'll talk about lots of cool stuff. You guys heard about AppSync. We announced it this morning, so it's a fairly new service. Right now, it's available in preview. There's a URL at the end. You go there. You can sign up for AppSync, and we'll give you access in a few days. But anyway, my name is Rohan Deshpande. I'm a senior engineer with the team. I'm the lead for this product. I've been at Amazon for about 6 years or so, worked on quite a few services, and this is pretty exciting. Not many people that get to launch a new service, and super exciting and fulfilling. And with me is my colleague, Michael Paris. He'll take over a little bit through the presentation, and we'll tell you guys some really cool things about building apps with AppSync. So, it's almost 2018, right? And if you want to build a mobile app, just want to build a mobile app, there's a whole bunch of things you have to do, right? There's four core things you really have to do. There's identity you have to manage, because you need to authenticate and authorize your users. And the AWS ecosystem, we highly recommend use IAM and Cognito. Those are the standard solutions. At the same time, the problem we have is, now there's so many devices, so many different form factors, so many variations in platforms, like even the Android versions are not the same everywhere. So you have to make sure that your app runs on all these different devices on platforms, because you want to go where your customers are, right? You can't tell your customers you must use a certain type of device. They will use what they want. You want to run business logic in the cloud, right? Like, it's very important to plan for success when you build an app. So in this case, you need to make sure you're running against a scalable, highly available backend. And so that's where services like Lambda and API Gateway and the entire serverless stack comes into play, because you can run at scale, you can scale up or scale down as traffic increases, and you don't have to worry about the infrastructure in that case. You really just focus on your application, and you know that the infrastructure will grow or scale down as you need to. And then I think the biggest problem really comes down to data, right? Data, even now, is very complex to manage in a mobile app. You need to deal with things like synchronization. So, if you're building like a game app, maybe you have a leaderboard, you need to synchronize the scores across different instances of applications where you may have a lot of people interested in the same scoreboard. At the same time, you have the one-to-one use case where, you have your mobile app, maybe it's an iPhone, but then you also want to synchronize the data on an iPad. So you want to make sure that the state, the user state, the application state synchronizes across all these devices. And then you have the problem of offline data. Your app should really work whenever you go offline or you have a poor network connection. Reason for that is users actually expect your apps to be functional even if you don't have great network connectivity. So the canonical example is you're in an airplane and you're in airplane mode, or you don't have Wi-Fi access, right? Some parts of your app should still work. If you're on a poor network connection, let's say you're driving and you're going through like areas where there's poor network connectivity, your app should still continue working without noticeable impact to your users. Because there's been a bunch of studies and a bunch of data that proves that if your app doesn't behave normally, no matter what the connection, no matter what the network state is, users really will have no problem uninstalling your app and will just go somewhere else and never come back. So you have that. Once you have to tackle offline data, then the next problem you need to deal with is conflict detection and resolution, right? Let's say you allow people to make updates while they're offline. What happens when two people make conflicting updates when the apps go online, and how do they resolve on the back end? Classical way people have done it, we deal with conflicts on the client, right? When something on the back says, hey, there's a conflict, and then you deal with it on the client. And the way you usually handle it, the easy way to handle it is to throw a modal to the user and say, here's a problem. You pick. You tell me what to do. That doesn't always work, because users don't always know what to do when they encounter a conflict. So it's important that you also be able to handle conflicts, detect them, and resolve them on the back end on the server side itself. And then you have different storage systems. You have NoSQL stores, you have relational stores, you have APIs that have unknown stores behind them. You have to get data from all these different sources, and you still want to be able to aggregate them, display them in your mobile app, hopefully without introducing complexity in the mobile app, right? For example, let's say you're calling from an SAP database. You don't want to have direct connectivity to the SAP database from your mobile app. You want to have some layer in between that does the transformation and the aggregation for you. And a newer use case, which has come about in the last couple of years, is the ability to get data real time. So whenever changes happen on the server, you want them to be distributed and sent down to like any interested client, which could be millions of clients as well, right? Take a very popular chat client, for example. You could have millions of people subscribed to the same room. So whenever someone posts an update or posts a message in the room, you want to send it to all those connected clients in a short amount of time. Now, building a scalable real-time system is not a trivial task. If anyone's tried it, I think you know what I'm talking about. So, classic way, how do we solve these problems right now? We use APIs like REST APIs, or we use SOAP APIs, right? So if you have a REST API, let's say we were building this dashboard. Let's say we wanted to build like a real-time dashboard that shows us where every purchase is happening across your retail enterprise across the globe. The way you would do it with the REST would be you would have a bunch of endpoints you would set up. So to build this kind of a dashboard, you want something like, hey, when a purchase happens, go record it somewhere. That would be your put or your post call. You want to be able to search by some geo range or some criteria because you want to be able to show your dashboard based on some criteria. Right? You usually have filters on it. If you're building it for the mobile client, though, you don't always have the same search interface available, right? Like more commonly, people set up a separate API or a set of APIs for just the mobile use cases. Because the reason is you don't want all that data coming back because you probably don't need it on the mobile device. You're trying to optimize for bandwidth and usage in that case. So REST is great because it's really trivial to set up. We all know how it works. We've used it for a while. It's just standard HTTP and resources. And there's a bunch of clients out there. Everything just works great. But from a mobile client perspective, there are quite a few problems with it. It's not easy to express relationships behind a REST API. So let's say you have data that's sitting in a Dynamo table and an Elasticsearch cluster. Yes, you can you can simulate joins in the REST API, but it's not the same as actually establishing and maintaining relationships between the data, especially across different data stores. Take an app where you're building a master detail view, right? On the master view, you usually want a list with just a subset of the information. And then when you go into the detail view, you want to drill down and get additional fields and have them show up in that detail view. It's not easy to do that with REST either because you probably would set up separate endpoints, or you would have to come up with some query language or some structure so you can pass in fields and then filter the data onto what you need. Query support in general, typically the way this is done, if you implement a search API, is you would come up with your own representation and your own DSL and use that to actually execute the search on the back end. And then with search, obviously, with queries, obviously comes how do you order the data that's coming back? How do you page through multiple pages of the data that's coming back? And then there's notifications. If data changes, tell all connected clients that are interested in that change that something changed and let them do something with it. This is not just tell me something changed. This is also maybe give me a view of the data that changed. And that becomes complex because not every client may actually have access or should be permitted to see the data that changed, right? So it becomes a fairly hard problem to solve. So, like I said, it's almost 2018. There are tons and tons of complexities, and it's really, really, really still painful to build a mobile app. So, I'm really wondering, is there a better way to do this?
There is. Hey, everyone. I'm Michael. Thanks for having me. So yeah, there is a better way, and we're going to talk about it. So we chose the better way to be GraphQL. So a quick little 0 to GraphQL in 60 seconds. What is GraphQL? It's a query language for APIs. So what does that mean? It's not a database. It's not a graph database. It's a protocol that you can use, or that clients can use, to extract information from a server, and it's really good at it. It's also a runtime for fulfilling queries with existing data. This is actually a bigger point than it sounds, because it means that it can be iterative. If I already have a huge infrastructure with a lot of data everywhere, I can add GraphQL on top of it and start building modern applications on top of legacy systems. And lastly, it's a strongly typed contract between the client and the server. And this is also a huge deal, because as we just mentioned, we have all of these devices and all of these clients across all these different form factors, and you want to have a consistent language for speaking with them. So, in short, It's a great way of client applications to interact with data. Here are a couple examples. So in GraphQL, there's 3 base operation types. There are queries that read data, mutations that write data, and subscriptions that are push data in real time. You can see that the language that's used between all 3 of these things looks, well, almost exactly the same, except for that first word. This is different than what you would see in like in an API yesterday, with if you have HTTP for your posts and your puts and your gets, then you have to figure out WebSockets and have a messaging protocol there. This gives you a standard structure that you can use across all parts of your application stack. So how does GraphQL work? The first step in any GraphQL system, or building a GraphQL API, is always to define your data model. So here you can see an example of what we call the GraphQL Schema Definition Language, or SDL for short. It's not a complete schema, but it gives you the basic pieces. So you can see at the top, there's a type query. That type query is going to be our root query type, which means that it's basically the entry point for all read operations that are going to occur in our application's graph. You can also see type to do. Type to do contains some pretty basic information, an ID, a name, description, priority, and due date. And then you'll see in a second that we can selectively choose that data. So what's next? After you define your schema, you can start writing queries. Something about GraphQL is that it's strongly typed, as I mentioned before, which means that all of your queries are type checked and actually don't execute unless they satisfy the type constraints. This is great for debugging. It prevents you from shipping applications with bugs. And it just also makes it really easy to understand what operations I have access to and what data I can get and push. So here's a simple example of a query. It says query get to-dos. I guess you can guess what that does. You'll notice that in this selection set, or what the little brackets right after get to do, only include the ID, the name, and the priority. That's different than what we see on the left. So the to-do item actually includes more information than we're asking for. And this is an important point. Because in GraphQL, whatever you request is exactly what you get. So if I included a different field in there, that's what my response would look like. And I can always have confidence that what I'm requesting for is what I'm going to get. So this is great. GraphQL is really awesome. It solves a lot of problems that you confront when you're building web and mobile applications. But there's still a complexity to it because there's still infrastructure and you're still managing large-scale systems. So what we did is we wanted to find a way to allow you to focus on apps and not infrastructure. And so we built this new service called AWS AppSync. So what is AppSync? AppSync is a managed and serverless GraphQL service. We allow you to connect to resources that live in your AWS account already, or we will actually help you provision those resources using the GraphQL schema as a template if you so choose. And that's important because you own your data always and get to benefit from the same security primitives that you've grown to trust with AWS. You can also use services like, for example, with DynamoDB, you could use DynamoDB streams and have all of the same interactions that you're used to having. We'll just lay a layer on top. It has built-in offline support with our client toolset. So we've built a bunch of client tools that make it really easy to get started with AppSync, and we've built it on top of existing open source tools that people are already using and love, and we've added offline and data synchronization on top. We've also built conflict resolution in the cloud. So as Rohan mentioned, there's a couple different methods here. You can choose either to let the client always win, basically just whatever was pushed last, I want that to be the correct item. You can choose that the server always wins. So basically, if I've identified an item and somebody else pushed the same thing before I did, we'd say, hey, no, that's not OK. We're going to reject your request because the server is the source of truth. You can also choose to have custom resolution strategies by using a Lambda account, or a Lambda function that we'll call out to. So basically, we will handle the conflict detection for you and then automatically route to your Lambda, so you can choose to operate on the data how you wish. You can merge the objects. You can choose one over the other, depending on your own business rules. It's got enterprise-level security features. This is something that I hope you've come to expect with AWS. It's one of our top priorities always. And it includes, we have a couple different authentication mechanisms. There are API key is the simplest and the fastest to get started with. You don't have to do much extra to get started with that. We also support built-in Amazon IAM, as well as that uses SIG v4 signing, to basically authenticate requests so that we always know who's making calls. And we also support Cognito user pools that can allow you to do more fine-grained access control with things like groups and some other cool primitives there. And then lastly, but not least, simple and scalable real-time synchronization. This is nice because you don't have to deploy servers or WebSockets or anything to scale your subscriptions and your real-time data. We'll do it for you, and we will allow you mechanisms to hook into it. So how does AppSync work? As I said, the first step is always creating and defining your schema. Your schema defines your data model. The schema defines the operations that you have access to, your queries, your mutations, your subscriptions, and that's always what you're going to do first. Next, you're going to be able to connect data sources. So these might be data sources that are already in your account. As I said before, we can help you provision these data sources. At launch, we support DynamoDB, Lambda, and Elasticsearch, and have a lot of capabilities around those three. And then lastly, you're going to use our client tooling or basically any open source GraphQL tooling to connect to our service and start implementing it in your application. You can build on iOS, on Android, React, React Native, IoT. We have an Alexa skill. There's a bunch of stuff that you can do. So I want to pitch an app. We're going to build an app that simulates if you or me or anyone in the room owned a brick-and-mortar retail store, and you wanted to have a real-time dashboard that showed you where purchases are happening in a geographic location at any given time. So step one, we need a robust, scalable storage engine. For this, we're going to use DynamoDB. It scales really well. It's reliable and low latency. We also need geospatial search. So I'm going to need to be able to say, I want all of the purchases that happened within 100 miles of this location within the last 60 minutes. We need real-time updates for both web and mobile. This is where GraphQL subscriptions come in. And the last piece is we need mobile and web clients, and more. But for now, mobile and web. These will be React and React Native. They will use an extremely similar programming model. And actually, we've seen that we can share a lot of the code between these applications. And make it really robust. So before we show you how we did it, we're just going to kind of lay out the diagram for what it might look like without a service like AppSync. You might have your web servers, or sorry, you've got your data. The data is living somewhere. You've got your Lambda that's doing your business logic, your DynamoDB instance that's storing the store of truth. It's where you're keeping your records for the long term. You've got Elasticsearch. It's your querying index. You can do geospatial indexes there. You can do all kinds of analytical queries there, make it really powerful. Just to show on the right, that's a symbol for a DynamoDB stream, streaming information into Elasticsearch. So every time the data operation happens on Dynamo, it automatically streams into Elasticsearch. You've then got a fleet of web servers. So this might run on EC2. It might be Lambda. It might be API Gateway. It might be ECS. Any number of these compute hubs. And then you're building a REST endpoint or a REST API on top of those. So that's listening to HTTP. It's taking puts and posts and gets and converting it into any number of different data stores behind the scenes. They're also going to have to talk to some pub/sub queue or pub/sub engine, like Redis, perhaps. And the web server is going to have to orchestrate that work as well. And then you're going to have another fleet of WebSocket servers that are sitting, listening to that pub/sub engine and pushing data over channels down to connected clients, which is a real scaling problem and is a difficult problem to solve. And then you've got your multiple clients that are talking to all of these different endpoints all the time and trying to make it work. So now we're going to show a demo. So we're going to go off the rails a little bit. So hopefully this works. Yep. OK. So here is our MapTap demo. Oh, let me just refresh it real quick. Move this guy around. So what we're seeing here is a map, if that was unclear. And you can see that we've had a couple purchases happening in Vegas or around the Vegas area in the last 60 minutes. Now, what happens if I want to do a query, say, OK, 100 miles is great, but I want it to be 1,000 miles? What happens then? So here it's a different query. So now you can see, OK, some people are buying some stuff back where we're from in Seattle and in Portland. You can see what's happened in the last 5 minutes, what's happened in the last maybe 24 hours. Ooh, that's a big one. There we go. And this will take a second. There's a lot of info. So there's a couple hundred objects that are about to come down to us. There doesn't look that many, but if I zoom in, I promise. There's a bunch. Oh, wait, where'd they go? OK, I guess not so many. OK, but that's the point. So here's our app. This is real-time, too. So when I click, I'm simulating a purchase. So every time I'm clicking, that's firing a GraphQL mutation through AppSync that goes to DynamoDB, streamed into Elasticsearch, and then I can immediately start querying it again. So I can go see what's going on over here. It'll change in a second. Let's see. There we go. You can see there's a bunch of information in here. Let's make this a little shorter. OK. So that's our application. So now we want to talk about how, why. How do we do this? So I'm going to take you in to the AppSync portal. This is our console. It's the quickest way to get started with AppSync. And I'm just going to walk you through a couple of the things that you need to do in order to build this app yourself. So first, I've got a couple apps in here. Some are marked with do not delete. I've got this map tap one, though. So this is your API homepage. Like I said with GraphQL, there's actually only ever one endpoint that you need. With a single /GraphQL endpoint, you gain access to your entire schema and have access to provide, you can start issuing GraphQL requests using the GraphQL schema or query language, and then that will be resolved by the AppSync servers. I've currently got API key enabled. So this is, as I said, the simplest authentication mechanism and authorization mechanism that we offer. Basically, you can just take this token, put it in the header, and then you'll be authorized. And then we've got some getting started steps. But more interesting, we're going to go to the schema page. So here's your schema page. And this is where a lot of your work will be done. You've got your types. Actually, before I go to this, let's go check out the data sources. So on the data sources page, this is another super important thing. So you can see I've got 4 data sources hooked up. I've got a AWS Lambda that's called the batch process Lambda. We'll talk about why that's relevant. We have a Lambda function that is just our process Lambda. That's like the one above it, except it only operates, it's not batched. We've got our Amazon Elasticsearch cluster that we called TapES. You can see that I basically have given it a simple kind of a name that we can use within AppSync, but then we've got access to the actual cluster itself. And then we have a DynamoDB table for our taps. So these are our 4 data sources. You can add more. Click New, kind of go through some DS, and then here you got access to your types, and then we'll actually fill this information in for you. I'm not going to add one right now, but here you can see we've got a lot of Dynamo tables in here. We can keep adding those. But let's first go back to the schema page. So let's take a look at our schema. So starting from the root, there's always going to be this root schema declaration here. This is where we define the entry points into our API. So I said there's only 3 operation types. There's query, mutation, subscription, and here's where we define them. So we're saying the entry point to our queries is the type query. The entry point to our mutations is the type mutation, and likewise for subscription. So here on query, it's down here. You can see what we have access to. So we're saying we're going to allow 2 major operations here. We have TapsNear, which takes a couple arguments, a location input that says where do we want to look for taps or purchases. We have a distance, which is just a float. So we're saying I want 100 miles or 100.5 miles or whatever it is. A distance unit, which we can see here. So this is a GraphQL enum that I've defined to coordinate to Elasticsearch's understanding of distance units. So this is straight from the Elasticsearch docs. Just added my own. And then we have an ago. That's how long ago do we want to look. And a time unit, which is itself also an enum, which is just MH or D for minutes, hours, and days. So that's great. That's our queries. We can do the same for mutations just to finish it up. So for mutations, you can see here's our type mutation. We have a single mutation. It's called tap. It takes a location and a timestamp, and it returns a tap. That tap goes to DynamoDB, is streamed into Elasticsearch. And you'll notice that I actually don't even give an ID in here. So that's another cool feature that we'll show off in a second. And then we have subscriptions, which is the same thing, except for real-time data. So we have a subscription called onTap that returns a tap every time a tap happens. This is called a directive. A directive is basically any annotation that you want to provide to either the schema or to even queries you can put directives on. This is one that we provide out of the box, and that's managed by us, and it's the mechanism that we use to allow you to subscribe to certain mutations. So the way that subscriptions work currently is that a subscription you can think of as a reaction to a mutation made elsewhere. So I can subscribe to GraphQL interactions. I'm saying every time you call the tap mutation, I want you to push data to all connected clients that are listening to the on-tap subscription. And that's how easy it is. All you have to do is this, and then you've got real time. So keep going through this. A couple other things just to note for completeness. We have an input. Input is a type in GraphQL that you need for if you ever want to pass an argument in, it has to either be a scalar or an input. So we're defining inputs for our types. We also have a type location that just holds lat and lon, or longitude, latitude, and a couple other things like a tap connection. This is something that you'll actually find is pretty common in GraphQL APIs. There's often ways of talking about standard ways to paginate through things, and the kind of agreed upon nomenclature thus far has been connection to refer to that. And then that's pretty much most of it. So this is our schema. And now we can kind of see, OK, so we've got our schema. That's our types. It's defining the structure of our API as well as the operations that we have access to. And then we have our data sources, which defines where is our data, what are our compute resources, where are we keeping our records. But there's not yet a line between the two. So that's the last thing, the third concept that's super important in AppSync right now, is that there's a concept of a resolver. So a resolver you can think about as a function that is attached to a field and that gets data. It goes and gets data to return for that field in the GraphQL execution. So to see that, that's what this right pane is for. So let's go look at let's look at the mutation tap. So here I can just type in mutation. So we've got this tap field, and I'll click on this resolver that we've already defined. So with your resolver, I said we're attaching it to a field, so resolver for mutation.tap. I'm going to choose a data source because resolvers depend upon where the data lives. This particular instance, it's the tap table. So that's a DynamoDB table that we had already designated is in our data sources that I showed earlier. And then here's the fun part. So we have the concept of a mapping template. A mapping template, there's 2 of them per resolver. One translates from GraphQL into the domain knowledge of that data source. And then the other, after that function executes and we've gotten our data back from the data source, the response template takes that result and returns it into the shape that GraphQL is expecting. So let me jump back real quick. So here we saw that we have the mutation tap. Tap takes 2 arguments, a location input and a timestamp. And it returns an object of type tap. So that means after our response template is done, we want it to look like a tap. So I'll go back to that. So here we go. So here you can see, OK, so we've chosen our tap table. We're giving this response or this request mapping template. The mapping template itself, we use a templating language called Apache Velocity, or VTL for short. It is, you can think of it as just another one of those templating languages. You are able to embed logic in it, and we actually give you a fair amount of helper functions that will call to our service and do certain things for you. For example, there's a super common use case of serializing some object to JSON. Like that's a helper function that we'd supply. You can also see an example of util.autoID. That's another helper that we provide that allows you to auto-generate UUIDs on the server so that your clients don't have to generate IDs themselves. And it's a super helpful use case. So let's step through this. So the first thing you see is this version tag. That's for us. That's so that we know how to parse this particular instance, because it might change in the future. But for now, it's just the version is set. Second thing you see is the operation. So operations are specific to data sources. This one is a DynamoDB put item call. I'm trying to create an item and put it into a DynamoDB table. That's called put item. So that's our operation. Depending on the operation, the rest of the data can vary. So for DynamoDB, it expects you to give it a key. So we have a DynamoDB table where the hash key is named ID. So then we're going to say that same thing and say the key is named ID, and I want the server to automatically inject a UUID every time I call this mutation, so I don't have to worry about IDs ever again. The next thing is you're seeing the attribute values. So here, I'm using my context. So this context is an object that we feed in to every time that we evaluate a velocity template, we feed in this context object, and it has some helpful things. I can pull it up from the docs on the right. So here you can see some of the things that we provide, just some basic docs. There's a quick reference that'll continue to grow. But at the top level, you see context.arguments. That refers, it's a map that refers to all of the arguments that were passed into that field in GraphQL. So remember I said our tap mutation takes a location and a timestamp. That's what our arguments is, which is why I'm able to call context.arguments.timestamp and fill that value in my DynamoDB call. There's one for identity. That is when we're logged in as a user via SigV4 with IAM or Cognito, that identity object will be filled with user credentials or user information that you can use. You can get the username, you can get the Cognito ID, things like that. Context.result is what you get in the response template after you've evaluated the request template, made the request to the data source, and it comes back. That will be filled in context.result. You can then manipulate that object to turn it into the shape that your GraphQL API is expecting. And then there's other utilities like toJSON, AutoID, and much more to come. So that's just a quick little note. So here, let's just finish this up. So we've got our attribute values. You can see the timestamp. You'll notice these S's and these M's and these N's. If you're familiar with DynamoDB, those will look familiar. It's a domain-specific language for DynamoDB. And you set it up once in this mapping template, and then your client developers never have to worry about it again. Once we set it up, it's good to go. And from your application standpoint, you're seeing tap. You're not seeing put item into DynamoDB with a hash table or with a hash key. And then the simple configure the response mapping template. This is a simple one. We're just taking the result and plugging it and pushing it back out using this toJSON result that's going to serialize it and allow it to go back down to our client. You'll also notice there's a couple helpers here. I'm not going to change it now, but there's a couple helpers that you can use to basically get you started. I know this might look like a lot, but I promise it's not that complicated once you get used to it. So we've provided a bunch of helpers here to get you started with really common use cases like pagination, queries from indexes, scans, delete items, get items by ID, all those kinds of things. And the same thing for response templates. So that's great. That was how we configured adding a tap to DynamoDB. So here, I can just go, and I'll just say mutation, tap, location, lat. Let's just put it at some ridiculous location that's not real. And then for timestamp, let's just say, I don't know, what is today? 28th? Oops. And then I click run. You can see I got back my ID. So that worked. That's just showing how that whole thing, this ID, I never passed in an ID, that auto ID was generating it for me. So now let's look at something a little bit more fun. So we have tap that allows us to put information into DynamoDB. We have taps that allows us to get information out of DynamoDB. But we also have TapsNear. So TapsNear is interesting because look at all the arguments it's taking. This is our geospatial query. So if I go down and look at TapsNear, I can click on our taps resolver, and this is going to look like a lot, but that's because it's full Elasticsearch. You have the full power of Elasticsearch at your fingertips. So here again, I chose my Elasticsearch domain as my data source. That was registered in the data sources tab. And then here, same thing. You see the version. That's us. You see the operation. Because Elasticsearch exposes a RESTful API, the operation is get. We're going to make a get request to this endpoint. The endpoint is a path of maptap/tap/search. That is an index that I created. So maptap is the index that we created in the cluster. Tap is the type, the mapped type in Elasticsearch's index. And then _search is the search URL for that particular type. And then in the params, you get the full power of Elasticsearch here. So anything you find in the Elasticsearch docs that you want to use, you can use. You can parameterize it using velocity and take arguments out of the GraphQL layer and pass it onto Elasticsearch. You can hard code values in here. You can do whatever you want, and it'll come back exactly like Elasticsearch expects it to. So here you can see I've got a query. I'm setting a size. I didn't put pagination on this endpoint, so I'm just saying I want up to 500 objects. We have the query clause where I'm saying Boolean, so true or false. Must, so both of this, like this has to be true. And then range is a way of doing a time query. So I'm looking for a range of times. And I'm looking at the timestamp field in my index. So you saw in my tap type in my schema, we had the timestamp field. That's what we're looking up. And then here I'm defining greater than or equal to a certain timestamp that I'm going to give them. So what you'll see here is now is an Elasticsearch concept that takes the server time at the time that Elasticsearch receives the query. And then here you can see where the parameterization is happening. So remember, I passed in that ago query, or that ago argument. This is a number, like 100. This time unit is the enum. This is either M or H or D, which means minutes or days or hours. So I'm saying now minus 100 minutes divided by, which means bucketed, so bucket to the unit. So this is saying I want now minus 100 minutes bucketed to the minute. So if you kind of fall in that weird middle ground of that minute, I want you basically to round down and include that in. And then the filter clause is where we're doing our geo query. So here we've got a geo distance query. We're looking at our location. So the distance is, again, very similar to what we saw in the timestamp query. It's I want, this center, from the center point, a number. So this is the arguments.distance is a number like 100. The context.arguments.dist unit is an enum value like m for meters, mi for miles, km for kilometers. And then a location, which takes the latitude and longitudinal coordinates that you want to be the center of that circle that we're searching. Of course, you can change this. So you can do geohashes. You can do strong polygon searches and all kinds of things. Everything that Elasticsearch has the power to do, you can do through GraphQL with AppSync. And that's great. So again, just samples. These are specific to the data source. This detects that it's an Elasticsearch data source. So we show you Elasticsearch relevant mapping templates to help you get started. And then we'll look at the response. So here's our first taste of velocity. It's, I'll show you why this is the case. So I don't want to jump too many times back and forth. But this is an example of what Elasticsearch would return for that given query. It's an object. It has some measurements like how long it took, if it timed out or not, how many shards did we hit, what were the hits, and then they ask the total number of hits, and then you get a paginated set within that set of hits. So this is all Elasticsearch, just showing you why we do it the way we do it. So it has this hits, so it's the object, the result. So this whole object will be context.result. And then we have to get context.hits, and then one more, .hits. And then the information that we actually want is this source object that's included in each element in that result.hits.hits array, right? But the problem is we don't want to have to call out to Lambda to do this. We don't want to have to go deploy a Lambda function and then pay for Lambda every time that this invokes and then have add latency to our requests and our resolvers. So we wanted to provide a way that allows you to do this on the server in flight. So it's fast and speedy and the latency stays low and it's less costly. So here's an example. That's the example. So then let's go back to here. So what we're doing is if we go back to the schema just for a quick second, our query, TapsNear, expects an array of taps or a list of taps. So we need the result after we've gone through our response mapping template to look like a JSON serialized array of taps. So we go back. Then what we're doing here, oops, sorry, wrong one. Go to the bottom. We're laying out the outer brackets of our array. We're then iterating. This is velocity. This is allowing us to put logic in our templates. We're iterating through each entry in context.result.hits.hits. We're then using this velocity helper. If velocity count greater than 1, put a comma, because you have to have a comma delimited list in JSON. And then we're simply just spitting out the source of that entry, which is what I showed you in the code editor. And then we're ending it, and then that's all good to go. So after we make the Elasticsearch request, we get back that large object, we iterate through it, turn it into a form that GraphQL understands, and then it's good to go. So I can go back here to queries and show nearest TapsNear. You can see the autocomplete here. So I'm going to go back to our lat1 lon1, and then we'll do, one second, you can see this is GraphQL. This is part of the benefit. As I'm learning what GraphQL is, I might not understand fully what's going on, but because it's a typed language and all queries are validated against that type system, it gives me super helpful helper methods or helper messages, just as if you were using a typed language in your favorite IDE. And I'll keep going, so I'll say location, and I'll say ago, I'll say 100, I'll say time unit, minute, it even new because it's in num, a dist unit, or distance, let's say 100, to make this miles. Oops, that's time units. And then a dist unit of miles, and then here, location 1. Yep, I'm going to go ahead, run that. Oh no. Okay. Well, I don't know what's on with that. But anyway, it should work. Let me see if I can do. That's the same thing here. So that's the same query that is running here. If I open up DevTools, you can see that it would have that. Okay. And okay. So that's most of the concepts that we've covered. I would want to do one more thing. Okay. So we haven't touched Lambda yet. So we've done the tap table, we've done the Elasticsearch cluster, but we have yet to show how Lambda hooks up. So this is an interesting one. So this processed Lambda, we're simulating as if a tap or a purchase, we wanted to call out per tap and call out to a third party saying, was this purchase completed successfully? Maybe we're calling out to a bank, or we're calling out to a credit agency, or whatever it is, something that we don't own. We just want to have arbitrary logic that goes and checks that thing and says, is it good or is it not? So you can see on our schema, our tap type has a field processed. That processed field, so no longer is this just on the root query or the mutation or the subscription. We're correlating this tap actually with the Lambda. This tap has this process Boolean, and then we've attached a Lambda to it. This Lambda is in our account. We basically are this is a same kind of request mapping template. The operation is called invoke. It probably does what you expect. And the payload is you can pass whatever information you want into the Lambda of your own choosing and of your own shape. And then the response is the Lambda returns true or false. So then we're just returning the response to JSON as a helper. So that's cool. We have that allows us to do find processing flags on taps. But the problem with it is that if I have a lot of taps and I query all of those taps and I ask for all of those taps, what is the processed state, then the way that GraphQL executes requests is it'll first call that list all taps resolver, get back a list of maybe 100 taps from Elasticsearch, and then for each of those taps, it's going to go in and call the processed Lambda per tap. So that's called the n+1 problem, because I made one request to get taps, I got back 100 items, and I made 100 Lambda requests to go get a value per tap. And that's no good. That's something that we wanted to solve for. So in GraphQL, there's this concept, or this way of doing almost per request caching that they call the data loader pattern. Now, data loader basically solves this problem in that instead of me saying immediately go resolve that tap and go fetch that value from Lambda, we say, OK, GraphQL runtime, be aware that I want to make this Lambda request, but don't make this Lambda request right away. Basically cache it or store it for a second, and then once you've finished executing the current depth of that query, go make one request to Lambda that batches all of them together. So that's what our batched processing does, the batched resolver. And let me show you that. So here, if I just go back to our tap, here it is. You can see I've got the processed. I've also got processed batch. Process is the n+1 problem. Process batch fixes it. And I'll show you the difference. So here we've got back just, this is the old one. It's just invoke arguments and then result. And then I'll show you the other one. The batched one is, did I pass it? There we go. Can you spot the difference? We changed the operation from invoke to batch invoke. And then the system itself understands how to batch those requests. The difference is the Lambda function that you write has to be aware of this. And we will send you, instead of just one item, one payload, we'll send you a list of payloads and tell you that the contract is, with this list of payloads, we want you to return the response in the same order for all of those payloads, and then we'll pass that back instead of having to call individually for each one. But the request and the response mapping templates work exactly the same way as if you were operating on a single item, which is really nice. So you can move between these things. If you find that there's an N+1 problem in your application and you need to fix it, it's as simple as changing that Lambda function to operate on a list instead of a single item, and then change that invoke to batch invoke, and you're good to go. So that's it. That's a lot of MapTap. And now what I want to do is invite Rohan back to the stage, because as we have this React application, we actually have a couple applications. We have React and React Native, and Rohan's going to show you the awesome work that's gone into making this multi-platform. Thanks.
Thanks, Mike. All right, thanks, Mike. So before I show you the React Native application, let's really quickly take a look at the code that we have with the React app. This is a standard React.js app. It's really just one file. It's app.js. That's all. You have your GraphQL queries defined here. Standard best practice, I guess, is you put them in JS files, and you import them, and you use them. But really in app.js, what you need to do is you instantiate your AppSync client. AppSync. Where is it? Oh, index. There you go. So you've set up your client over here. This is using, so the AppSync client is built on top of the open source Apollo client, so it uses HOCs. And you're down here, and all you're really doing is you're composing your GraphQL, you're running queries. Here's how you set up subscriptions. This is how you trigger mutations. So it's pretty standard. So let's take this app and let's convert it to React Native app, because mobile is cool. And we want to see maybe a view every time someone purchases something. We want to be able to see it on a device. So let's go here. Let's run it. It's not cool. OK. So I have a React Native app here. Pretty easy. I'll tap here. What happens is this is going to write to using the same tap mutation, and you can see the events as they're triggering. And it comes back with, if it's green, it means that the Lambda function said that, yes, this transaction was processed. Red means it wasn't processed successfully. If we go back to the map app, let's refresh it. So let's tap at a random location here. You'll see this is hooked up with real-time subscriptions, right? So now anytime I tap on the map app, let's pick a city, let's pick Boise, for example, and it's sending a real-time notification. The app is interested, and it gets the update, and it goes and navigates to that location. So this is pretty cool, because really the way you set up subscriptions, like Mike showed you, was you add a single directive in your schema, and you get all this functionality just out of the box. Classic way you do it is you set up a pub/sub service, you have WebSockets, there's a whole bunch of things to manage. You don't have to do that anymore. It's actually one GraphQL directive, and it gives you this power and this flexibility. So looking at the code for this app, again, single file, right? So this would be just the React Native code, where you've written the code, you've got, you're handling a tap event, you're setting state, and then this is your view definition, right? This is quick and easy. And so if you want to add AppSync into it, again, it's the same thing. You instantiate the AppSync client, you define your mutation in your query, right? This is exactly the same as you would see in, as you saw in the React app. What do I do here? OK. And then you hook up your mutation. So this is when I tap on the map in my native app. I'm triggering a client mutation with the parameters. So when I tap on the map, it takes this native event, gives me the coordinates, and I can send that to the server with a timestamp. And I update my local state optimistically, because I want to show the tap to the user. Because if I was offline, I don't want them to feel like they tapped and nothing happened. I want to give them an optimistic update. If I was offline, it what the AppSync client that we provide actually does is it will cache your write. It will cache the actual update. When you come back online, it will send it to the server, and then depending on how you set up conflict resolution, it may or may not actually end up committing and get distributed to every client that's connected to it. And then for subscriptions, again, we just hook it up in component.mount. It's really this couple of lines of code here. You're hooking up the hydrated client to subscriptions, and then you're saying anytime I get data, set my state, and then go and navigate my map to some other location. So, you can share a lot of this code. In fact, commonly what you would do is you would take a lot of this GraphQL code, share it as a common JS function or library, and use it in your React app, React Native app, wherever else you want to use it. So it's pretty easy to get started, get like all the functionality of AWS, all the power of AWS, and the scalability and the availability that you need with a couple of lines of code, a couple of directives, and your app can basically scale as wide as you want it to scale. So this is cool. Let's say we want to simulate a process. Let's say we want to do this through a Lambda function. Let's emulate a process where we're saying, hey, I have a bunch of stores, and they're sending a bunch of events because people are purchasing. So let's emulate that and maybe write it as a Lambda function. So again, what I want to show you in the Lambda function is we're doing the exact same thing. We're hitting the same AppSync API backend that we have. We're using a different library in this case. We're not using the AppSync library. And this, you can use any open source GraphQL library because guess what? AppSync's endpoint is completely GraphQL compliant. So use anything you want. We're using this GraphQL request library in this case, passing in the API key as a header because that's my identity, using the same exact mutation here. I have a little function which gives me random coordinates for latitude and longitude. And then all I'm doing is I'm passing it in as a request object and saying, go do things. So if I run this, so the way I'm running it is it'll pause every 2 seconds, but it's invoking the Lambda. And it's not very smart. It'll just make random coordinates come up. But every 2 seconds, it'll go and trigger the Lambda, which then goes through AppSync, and you'll see the app is actually navigating to that location. So far, it's picked ocean because I guess we have a lot of people purchasing from the middle of the ocean, but I think that's cool. OK, so we've got Lambda. We've got React. We've got React.js. We've got React Native. So we've got cross-platform across browsers and mobile devices. And then we can do this from Lambda as well. So as a backend process, what's really cool is your AppSync endpoint is not just for clients, right? You can actually use it for server-to-server communication and data aggregation. So a common use case is, hey, you have data sitting in DynamoDB, but you also want to run rich queries through Elasticsearch. It doesn't always have to be a rich client or a client you distribute to your customers. This could be a service calling another service, which is then actually abstracting away your backend stores. So let's kill this. The new hotness is voice-controlled interfaces, right? So Alexa and Lex and that like of things. Can we hook up GraphQL to maybe trigger through an Alexa skill? Well, let's check it out. We've got the same exact interface, and let's see. All right, there we go. OK, so this is, EchoSim is it's a skill testing tool. So if you don't have it in Alexa, if you're trying with different accounts, you can use this guy to make sure that your skills are working. Let's see. So what I've got is a skill that's triggered by the keyword AppSync. And I've never tried this on stage, so we'll see how this goes. Alexa, tell AppSync to purchase. OK, doing its thing, doing its thing. Purchased. Oh, look, there you go. So what happened was this actually invoked the same Lambda that was running through my command line, generating a random event, random latitude, longitude. And it then sends it to connected subscribers, which in this case is my mobile app. But if I had zoomed out here, I have no idea where I'd put it, but somewhere here. It's somewhere on the planet. It definitely sat somewhere on the planet. So cool. So what we've done is we've built a cross-platform backend that's leveraging a bunch of data stores and functionality through Lambda And it works through basically any interface, any client you can think of using GraphQL. So let's go back. All right. So this is what the architecture looks like now, right? If you remember the previous slide, we had a bunch of infrastructure we were running. We've replaced our PubSub fleet, replaced our WebSocket fleet, replaced the API fleet with AppSync in there. You get scalable, secure services, highly available services just by using AppSync as your service that you use to go talk to your data sources. So the way the flow works in this case, we have an Alexa skill or a browser or a mobile device, doesn't matter. They all talk to the same GraphQL endpoint. What AppSync does is it actually takes the GraphQL request, converts it to whatever the downstream data sources that you're trying to query or write to. In this case, we were writing to Dynamo. We had Dynamo streams going through a Lambda, putting stuff into Elasticsearch. And so you could run rich queries against Elasticsearch. And then we had Lambda emulating a third-party service, which was basically saying whether your transaction was processed or not. So simplifies your stack. You get a managed service. You don't have to worry about infrastructure. You don't have to worry about scaling, which I think is pretty important because your app could take off very quickly. At the same time, you don't want to provision a bunch of infrastructure planning for that level of success either, right? It's expensive. So reiterating the benefits. AppSync uses GraphQL, so your clients can request just the data they want. You get nothing more, nothing less. This is pretty cool because you actually control the bandwidth usage. You can get data from many resources with a single request. Again, this is super important because you may have different data sources, different tables, disparate data sources. And so a single query, we're using the right resolvers or using batch resolvers to solve n+1, you can get data in a single request without actually letting your application be aware of all these different data sources, right? So you get a very simple common interface. Your front-end developers control the actual interaction with the service, and then you don't have to worry about the backends themselves. Documenting APIs is pretty cool with GraphQL as well because most developers, me included, don't really like writing documentation. What GraphQL does is it actually lets you write inline documentation, which shows up automatically in the tool using introspection. So this is pretty cool because you can actually very quickly document APIs and make sure that the next person that's coming along and using API has great documentation they can use to continue. Has a strong type system, which again lets you validate requests as they come into your GraphQL endpoint, so you know that you're not going to be servicing arbitrary requests. You don't have to worry about things like SQL injection. This is also great because from a client perspective, whenever you're developing, there's actually tools that can understand the schema. They can validate the code you're writing at compile time, which improves type safety, improves your code, reduces bugs, and you can actually operate against the AppSync endpoint, against the GraphQL endpoint, using a strong type system. And finally, it helps with simple API evolution. Backwards compatibility really isn't that much of a problem anymore because you have a single API, but your API basically works on types, not on separate endpoints. Like REST endpoints, what you would do is if you wanted to version it, you would stand up yet another version with a different version header or something, some way to identify it. But the GraphQL, you just keep evolving the types based on the fields you need. And then your clients actually own the response structure, the selection set that's coming back. Which help, so you can, on the server, you can actually use that to determine if some fields are being used, so you can deprecate them, get rid of them. You have a lot of flexibility on the server side. So that's all we have. It's a new service. We would love for you guys to use it, give us feedback. You can sign up at awsamazon.com/appsync. It's a preview service, so submit a request, tell us what your use case is. We're looking at these very frequently, and we'll get back to you with access as soon as we can. And that's all we have. Thank you, guys. You've been great.